Hello students and welcome to the 25th lecture on particle physics, and today we are going to talk about CPT symmetry, where we have charge conjugation, parity and time reversal, all three together. Now CPT symmetry asserts that the laws of physics remain invariant under simultaneous transformation of charge conjugation, parity and time reversal. And the order is not important, whether you apply first C and then P or T, or when you apply first T, time reversal, then parity and then charge conjugation, the end result would be the same, as we have seen in the case of CP or PC operation, whether we apply parity and then charge conjugation, or first we apply charge conjugation and then parity. Now, in some simpler terms, if you observe a particle interaction and then replace the particles with their antiparticles, invert the spatial coordinates, that means replacing r by minus r and momentum by minus p, etc., and reverse the direction of time t to minus t, the resulting physical processes should be indistinguishable from the original. CPT symmetry has profound implications, suggesting that any violation of one of these symmetries, either C or P or T, must be compensated by violations in the others to maintain the overall CPT invariance. For example, yesterday we were discussing about CP violation in the neutral kaon sector or B sector, or some evidences in the D sector. Now, if CP is violated, then T has to be violated such that CPT is conserved. Therefore, violation of T would imply that CP has to be violated. Consequences of CPT conservation is that particle and antiparticle should have the same mass. That means mass of electron is the same as the mass of positron, mass of proton is the same as the mass of antiproton, and so on. Particle and antiparticle should have the same lifetime. For example, if we say that neutron's lifetime is 890 seconds approximately, then antineutron will also exist for 890 seconds, and then it will decay to antiproton, etc. Or if we say that electron is a stable particle, then positron is also a stable particle. Similarly, for pi plus and pi minus, because pi plus is the antiparticle of pi minus. Particle and antiparticle should have the opposite charge. We have talked about proton's charge as +1 and antiproton's charge to be -1, positron's charge to be +1 and electron's charge to be -1, and so on. And particle and antiparticle should have the same magnitude of the magnetic moment. Only there will be a change of sign, and that will be because of the change in the sign of the charge. Now, experimental tests consistently support CPT symmetry. That means still now we have not seen any signature of CPT violation, while we have seen for the CP violation, affirming its crucial role in our understanding of particle physics and the fundamental nature of the universe. And in the standard model of particle physics, CPT is assumed to be an exact symmetry, and therefore CP violation would imply T violation. Now, till now, the difference in the mass of the positron and electron averaged over the mass of electron and positron has been found out to be less than, this difference is less than 10 power minus 9. Similarly, difference in the charge is less than 10 power minus 8. Difference between proton and antiproton's mass has been found out to be less than 10 power minus 10. Similarly for the charge, And similarly, we have the difference in the lambda and anti-lambda mass to be very small, almost negligible. Now, yesterday we were discussing about the CP violation and matter antimatter asymmetry. The CP symmetry is violated in certain processes, as we have discussed, that in neutral kaon sector it was discovered in 1964, and in recent years it has been observed in neutral B sectors, and as well as there are strong hints in the case of D sector as well as BS sector, where we have a strange component also with the beauty quark. But the CP violation in the quark sector is very small and cannot explain the present matter antimatter symmetry. And a dynamically generated matter antimatter asymmetry of the universe requires additional sources of CP violation, and such sources are naturally generated by the extension of the standard model of particle physics, and that is what we call as beyond the standard model. Now, CP violation in the lepton sector is expected to give more information, and for this, neutrino experiments are going on, as well as they have been planned with, where one is trying to study CP violation in the lepton sector. Therefore, neutrinos are promising particles which can give us information about CP violation in the lepton sector. Now, what we know about the neutrinos, that there are three generations of neutrinos. One is the electron family, the other is muon family, and the third is tauon family. Now, we assign independent lepton number to this, muon number to the second generation, and tauon number to the third generation. Then we have antiparticles, positron and antineutrino, mu plus and nu mu bar, and tau plus and nu tau bar. And here the lepton number is -1. And independently, in the standard model of particle physics, these lepton numbers are conserved for each generation. We have independent electron lepton number, muon lepton number, and tauon lepton number. The important point is that these neutrinos are coming from the various sources in the universe, and it is the most abundant particle after the photons, but they are least understood. This is because neutrinos are weakly interacting particle. Their cross-section for neutrino electron scattering is around 10 power minus 40 centimeter square, while if we talk about the strong interaction cross-section, that is around 10 power minus 24 centimeter square, or 10 power minus 26 centimeter square, or in general we say that it is of the order of barns, while electromagnetic interaction cross section is of the order of microbarns. And here the cross sections are very small, and therefore these particles is extremely difficult to observe, and never we can observe a neutrino. Always the indirect evidences tell us about the existence of neutrinos in the vicinity. Now, these neutrinos are coming from sun, they are coming from the cosmic rays, they are coming from the supernovae burst, etc., etc., that we will talk about in the next lecture. Now, the most important property associated is that with the neutrinos is that neutrinos oscillate. They change from one flavor to another flavor. We start with a muon neutrino beam, and at the end we are observing a particle like electron in the final state, which would imply that a neutrino, electron type neutrino has interacted with the target, and therefore on way a nu mu has traveled into nu e. That means we have millions and trillions of nu mu's. Among them, a few have got converted into electron type neutrino. Similarly, solar neutrino puzzle tells us that the amount of electron type neutrinos those should reach to us is smaller than expected from the standard solar model which was given by Behkal and his group. And similarly, from the cosmic rays, we expect the muon type neutrinos to be in the ratio of 2:1, where 1 is for the electron type neutrinos, but experimentally it has been found out to be in equal proportion, and this is what we call it as on way when a nu mu or nu e travels, they oscillate into other flavors, and this oscillation is given in terms of oscillation probability. Now, what do we know about neutrinos? That all the neutrinos are left-handed particles. That means their momentum and spin are oppositely directed. Then we apply charge conjugation operation. When we apply charge conjugation operation changes a neutrino to anti-neutrino, and that means this anti-neutrino is also left-handed, which has not been observed. But when we apply P operation, parity operation, that takes P to minus P, then what we observe that these anti-neutrinos have become right-handed. Therefore, C and P together gives us an evidence that we get from neutrinos anti-neutrinos. Okay, and similarly we have, as discussed, that we have Keon regeneration, where what we discussed in the last lecture, that we start with a pion beam which strikes a proton target, and we have lambda 0 and k0 in the final state. This k0 travels while it propagates as k10 and k20, some admixture of these two propagation eigenstates. These propagation eigenstates, we are calling it by the name k10 and k20, which in turn we re-christian the name by the name kl0 and ks0, and ks0 decays but kl0 survives. KL0 has both the components k0 and k0 bar. Then we saw that we get some evidences which can only be obtained when a k0 bar beam is present in the pure beam of k0, and that is why we have a lambda pi plus strong interaction events with a k0 bar beam, which is not possible with a k0 beam, and this we call it as Keon regeneration phenomena. Similarly to this, we talk about neutrino flavor oscillation, where what we do, we have a proton beam. This proton beam strikes, say, graphite target. This is a graphite target, and we have pions and kaons, or pi minus and k minus. These particles are there. Then we apply magnetic horns to select that whether we want pi plus k plus particles or pi minus k minus particles. Now, depending upon the magnetic horns, we choose pi plus, say for example, and k plus. Now, this pi plus k plus, they are short-lived particles. The magnetic horns will ensure that these particles are traveling in the forward direction. Now, after some time, they will decay into mu plus and nu mu. Now, that means from protons striking graphite target, we are producing pions and kaons, and these pions and kaons, they are traveling in the forward direction, and after some time they decay into muon and neutrinos, or similarly we can have mu minus and nu mu bar if we speak about pi minus or k minus. Now, if we have a nu mu that is traveling and we observe an event at the other end as E minus plus P in the final state where we have a nuclear target placed before this neutrino beam, then this can only happen because of lepton number conservation. A nu E is obtained from a nu mu beam, and what we say that actually this nu mu does not travel like K0 or K0 bar, they do not travel, but what propagates is K10 and K20. Here what we say that this nu mu is some admixture of nu1 and nu2 mass eigenstates. These are the mass eigenstates, and nu mu and nu e we call them by the name flavor states. Therefore, we have flavor states and nu1 and nu2 are mass eigenstates. Now, if we in general talk about all three flavors of neutrinos, then we have alpha nu1 plus beta nu2 plus gamma nu3 that we will discuss in the neutrinos lecture when we will talk about neutrino oscillation in great detail. Then what we are talking about that this nu1 and nu2, they have got different masses, like we had the mass difference between MKL and MKS that we found out that this is of the order of milli electron volt. Here also we say that there exists at delta M the mass difference between neutrino mass eigenstates M1 and M2, and because of that these nu1 and nu2 are not in the same phase, and therefore when they propagate there is a chance that we get a nu e at the right position that we will talk about. Neutrinos of certain energy, they are giving us nu e starting from a nu mu beam. That will depend upon how much nu mu has traveled from the production site where pions have decayed. Therefore, this is what we are talking about, that protons are striking graphite target, pions are getting produced. Through magnetic horns, we are focusing these pions such that we have neutrinos in the forward direction, and then these neutrinos are traveling in the as the composition of mass eigenstates instead of the flavor states nu mu or nu e, and then while it propagates, finally what happens, we are finding out that among some trillions of nu mu's, a few of them have got converted into nu e, and there we called it as Qion regeneration. Here we call it by the name neutrino oscillation. Therefore, this neutrino, there are three flavors of neutrinos in the standard model, and here we are talking about the change of flavor of neutrinos from nu e to nu mu to nu tau, or nu tau to nu e, or vice versa. And this depends upon the oscillation length, and this depends upon the difference in the mass square of the mass eigenstates of these neutrinos, as well as the amount of mixing that is there. That therefore neutrino oscillation is purely a quantum mechanical phenomena in which neutrino created with a specific lepton number, either electron or muon or tauon, can later be measured to have a different lepton family number, and this oscillation probability we will learn in the next unit. That is given by sine square 2 theta times sine square 1.27 delta m square, L in kilometers, E in GeV, where theta is the mixing angle. It defines how different the flavor states are from the mass states. If theta is 0, that means the flavor states are identical to the mass states. Therefore, nu alpha to nu beta stands for, say, for example, nu mu to nu e, or nu mu to nu tau, or similarly you can think of the other combinations. and delta m square is the mass difference that I am talking about. Now, if there are two flavors, there will be two mass states, m1 and m2. This parameter is the difference in squared masses of each of these states. Delta m square is m1 square minus m2 square. For neutrino oscillation to occur, at least one of the mass states should be non-zero, such that you have a finite delta m square. Otherwise, if delta m square is 0, you can see that the oscillation probability from one flavor to another flavor will be 0. And this is what we are talking about, that this is purely a quantum mechanical phenomena, and the quantum mechanical phases of the two neutrino mass states advance at slightly different rates, and that is why to start with you have nu mu, and then after certain length you have nu e, and then after certain length you have again nu mu, and so on. And this happens for a few neutrinos, not all trillions of neutrinos which are coming to us. They will get converted, but few of them will get converted, and this is what we talk about. Say here, this blue line is representing, for example, nu mu, and this red line is representing, say, nu e. Then to start with, we had all the nu mu's with us, therefore the probability is 1, and then when it is propagating in space, as you can see here, we are writing L by E. This L is the oscillation length, how long it has traveled, and E is the energy of the neutrino. And we have seen in the expression for the probability that this is L upon E, where L is in kilometers, E is in GV. And then you can see that initially you had 0 nu E, and then gradually with oscillation length you have a mixture of nu E and nu mu. Somewhere nu mu dominates, somewhere nu E dominates, but at the same time probability of nu mu to nu E plus probability of nu mu to remain as nu mu, this should be equal to 1 to conserve particle number. If we talk about 3 flavor neutrino oscillation, then we will have nu mu to nu tau also in addition to these two. This is what we call by the name neutrino oscillation. Now let us come back to CPT symmetry. CPT symmetry in neutrino oscillation is closely related to the conservation of total lepton number, which includes the number of leptons such as neutrinos and the associated anti-leptons. Now we were talking about CP. Now CP, what I told you, that for example if I have left-handed neutrino, whether it is electron type or muon type, and if I am operating by CP, then observe one, we are finding out right-handed anti-neutrino, where momenta gets changes the direction and particle becomes anti-particle. Now conservation of CP would imply that the oscillation probability of nu mu to nu e would be the same as the oscillation probability for nu mu bar to nu e bar. That if CP is conserved, then all the parameters for nu mu to nu e oscillation would be the same as for nu mu bar to nu e bar oscillation. But when we talk about CPT conservation, then that means we have to also see T2 minus T. This would imply that if we talk about CPT, then oscillation probability for nu mu to nu e would be the same as the oscillation probability. Now you see, this is CP. When we also apply T, then we have nu e bar to nu mu bar. Therefore, the oscillation probability for nu mu to nu e would be the same as the oscillation probability of nu e bar to nu mu bar. And this is, any deviation from it will tell you about the CPT violation. Here, any deviation from this would give you the idea of CP violation while observing neutrino oscillations. That is why several experiments are going on to study CP violation in the lepton sector, and in the longer run of these experiments, since neutrinos experiments are very difficult to perform, therefore it's quite challenging. You need gigantic targets of the order of 1 megaton of water, for example, or 40 kilotons of argon target, or so on. You need huge amount of targets, or that means protons and neutrons, to have significant number of neutrino events. And really these experiments are very difficult to perform. Now, according to CPT symmetry, the masses and mixing parameters governing neutrino oscillations should be the same for neutrinos as well as antineutrinos. This is what we have discussed. Experimental evidence from neutrino oscillation experiments, including those conducted with solar neutrinos, with atmospheric neutrinos, with accelerator neutrinos, the one which I discussed where we had proton being striking graphite target producing pions, these are known as the accelerator experiments. But while sun is giving us neutrinos, they are by nature. Cosmic rays are striking Earth's surface, those are by nature. By comparing the oscillation patterns of neutrinos and antineutrinos, scientists have found no significant violation of CPT symmetry in the neutrino sector, while efforts are going on further to have precise results. Now, CPT conservation in neutrino oscillations has important implications for our understanding of particle physics and the behavior of fundamental properties. It reinforces the idea that neutrinos and antineutrinos are two sides of the same coin. If we find that oscillation probability for nu mu to nu e is the same as nu e bar to nu mu bar, and we are conserving CPT, this is implied that neutrinos and antineutrinos are two sides of the same coin, where their differences arising primarily from their distinct flavor content rather than from inherent disparities in their mass or mixing properties. Therefore, this can only happen where mass and mixing properties would be the same for particle and antiparticle. Now, the study of CPT symmetry in neutrino oscillation contributes to the broader exploration of the fundamental symmetries that govern the behavior of particles in the universe. As we have discussed, that why we are living in a matter dominated universe, where those antimatter have gone, and scientists think that matter and antimatter should have been created in equal proportions at the birth of the universe, just after the Big Bang. Yet when the two interact, they annihilate and gives pure energy. This kind of asymmetry is fascinating. We are living in a matter dominated world. It makes us want to know, how did this imbalance arise? Neutrino scientists are looking for something called CP violation to tell us about this lepton asymmetry in the universe. And that means, does the universe treat the matter and antimatter particles identically? If we observe no CP violation, then that means really there is some other reason for the matter dominance in the universe, because what we have discussed in the last class, that in the quark sector this CP violation has been observed to be very small. Scientists know neutrinos change flavor as they travel, a phenomena known as neutrino oscillation. And you know that in the 2015 Nobel Prize, this was awarded to two people. One was the director of Sudbury Neutrino Observatory, MacDonald, and another was the group head of Super Kamiokande Laboratory in Japan, Professor Takaki Kajita. And Professor MacDonald and his group was involved in the study of solar neutrinos, while Professor Kajita and his group was involved in the study of atmospheric neutrinos, and both of them confirm that solar neutrinos, for example, they oscillate, or atmospheric neutrinos also, when they propagate in space, they oscillate. And therefore, for the observation of neutrino oscillation, they were awarded on behalf of the Super K group and on behalf of the Snow Lab. They were awarded Nobel Prize. And if neutrinos do oscillate, this implies that at least one of the mass eigenstates state is non-zero if we consider two flavor neutrino oscillation, or if similarly if we extend this to three, then what we are talking about at one is massive. Scientists already know that CP is violated for one major building block of the universe, that is the quarks, and we have seen in the neutral kaon decays or B decays. However, this discrepancy is not enough to account for the matter-rich world that exists around us. If CP were also violated among neutrinos, it could point us towards this answer. And this CP violating asymmetry is given by the probability of nu mu to nu e oscillation minus nu mu bar to nu e bar oscillation, as we have discussed earlier, upon the sum of the two. This asymmetry, a non-zero value, will tell us that this oscillation is different for the neutrinos and anti-neutrinos. That means oscillation parameters and mixing, they are different for neutrinos and anti-neutrinos. This can not only be observed for nu mu to nu e and nu mu bar to nu e bar, but also if you consider where you have pure nu e beam, nu e to nu mu, for example, those are coming from the sun, or versus nu e bar to nu mu bar. Therefore, this, either you talk about this or you talk about this. If you observe this asymmetry, then that means equivalently I can tell you that nu L to nu L prime minus mu nu L bar to nu L bar prime upon nu L to nu L prime plus probability of oscillation of nu L bar to nu L bar prime, where L can be E or mu or tau, but L is not equal to L prime. That means if you choose L equal to mu, then L prime will be tau. If you choose L to be tau, then L prime can be mu or E. And this asymmetry, any non-zero value, will tell you about the CP violation in the lepton sector. And then if we include T also, then what will happen? This guy will give us nu e bar to nu mu bar, and then asymmetry would be defined as nu mu to nu e minus nu e bar to nu mu bar upon nu mu to nu e plus the oscillation probability of nu e bar to nu mu bar. And this non-zero value will also tell us about the CPT violation. Therefore, in the lepton sector, first people are trying to see CP violation in the neutrino sector and then extending it to CPT, where they want to compare nu L to nu L prime versus nu L prime bar to nu L bar. But these are the experiments which are quite challenging, and in the future we are going to have many experiments which will study neutrinos oscillation. Therefore, in the next lecture we are going to introduce neutrinos, which are really fascinating particles, and around us trillions of neutrinos are coming and we must try to understand them. Thank you very much.